We often talk about how much energy is in a compound or in a bond, but how do we know this? One way that energy is determined is through calculating the molar heat of combustion. The molar heat of combustion is how much heat is released when we burn 1 mole of a compound. Typically, this is set at a specific pressure of 1 atmosphere. The reason this works is because one form of energy is heat, so we assume that all of the energy is converted into heat. To measure the heat of combustion, a calorimeter is used. A calorimeter is an isolated system where all of the heat transfer can be monitored. When you start a bonfire, the wood is burning and the energy from the bonds is changed into heat. But because the heat escapes into the environment around us, it's really difficult to measure all of the heat change. So a calorimeter uses an enclosed system in order to measure the change in temperature. Typically, the calorimeter is filled with water, and the change of temperature in the water is measured. Water is used because we know the specific heat of water. In other words, we know how much energy it takes to increase water by 1 degree Celsius. And it is a cheap, easily accessible medium. The heat of combustion is calculated by multiplying the mass of the water times the specific heat of the water times the change in temperature. This entire equation is multiplied by -1 because heat of combustion is negative because heat is being lost or released. Delta H equals negative mc delta T. To measure the change in temperature, a bomb calorimeter is used. A bomb calorimeter insulates the water so that all heat from the burning sample can be accounted for. A bomb calorimeter has a water bath with a stirrer and thermometer inserted. In the center of the water bath is the bomb cell, which contains the sample and an ignition source. The initial temperature of the water is recorded. Then, the sample is ignited. The final temperature of the water is then reported. Then, we can use the heat of combustion equation to determine the energy in the sample. Let's look at an example using ethanol. First, it's set up with 100 grams of water in the water bath. We record the initial temperature as 25 degrees Celsius. We then add 1 gram of ethanol to the bomb cell and ignite it. The temperature of the water increases up to 95.91 degrees Celsius. 95.91 minus 25 equals 70.91. So the change in temperature is 70.91 degrees Celsius. The specific heat of water is 4.2 joules per gram degrees Celsius. Here is the heat of combustion equation for ethanol. Change in heat equals negative 100 grams times 4.2 joules per gram degrees Celsius times 70.91 degrees Celsius equals negative 29,782 joules. The heat of combustion of 1 gram of ethanol equals negative 29,782 joules, or 29.780 kilojoules. 1 gram of ethanol is equal to 0.02 moles. Typically, molar heat of combustion is given as kilojoules per mole, so 29.78 divided by 0.0217 equals 1,370 kilojoules per mole. We've already looked at ethanol, an alcohol attached to 2 carbon atoms. So now we'll look at an alcohol attached to 1 carbon, 3 carbons, and 4 carbons: methanol, propanol, and butanol. In our bomb calorimeter, we have 500 grams of water, and each of our samples will be 1 gram. Let's look at the change in temperature for these. Methanol, 10.89 degrees Celsius. Propanol, 16.04 degrees Celsius. Butanol, 17.22 degrees Celsius. Here are the heat of combustion equations for these alkanols. Methanol, change in heat equals negative 500 grams times 4.2 joules per gram degrees Celsius times 10.89 degrees Celsius equals negative 22,869 joules. Propanol, change in heat equals negative 500 grams times 4.2 joules per gram degrees Celsius times 16.04 degrees Celsius equals negative 33,683 joules. Butanol, change in heat, equals negative 500 grams times 4.2 joules per gram degrees Celsius times 17.22 degrees Celsius equals negative 36,162 joules. Now, let's change joules to kilojoules and divide that by moles. Methanol, negative 22,869 joules equals negative 22.869 kilojoules. 1 gram of methanol equals 0.03125 moles. Therefore, negative 22.869 divided by 0.03125 equals negative 731.8 kilojoules per mole. Propanol, negative 33,683 joules equals negative 33.683 kilojoules. 1 gram of propanol equals 0.0167 moles. Therefore, negative 33.683 divided by 0.0167 equals negative 2,016.9 kilojoules per mole. Butanol, negative 36,162 joules equals negative 36.162 kilojoules. 1 gram of butanol equals 0.0135 moles. Therefore, negative 36.162 divided by 0.0135 equals negative 2,678.7 kilojoules per mole. Let's put all 4 of our samples in order. Methanol, negative 732 kilojoules per mole. Ethanol, negative 1,370 kilojoules per mole. Propanol, negative 2,017 kilojoules per mole. Butanol, negative 2,678 kilojoules per mole. You'll notice that from one to the next, the heat of combustion changes by about 650 kilojoules per mole. This is because the heat of combustion for CH2 is about 650 kilojoules per mole. Each alkanol has an additional CH2 added onto it, so it gets an additional 650 kilojoules per mole of energy. The molar heat of combustion measures the amount of energy in a compound by measuring how much energy in the form of heat is released when the compound is burned. A calorimeter is used to measure the heat of combustion. Commercially, a bomb calorimeter is used. This puts the sample in a bomb cell in the middle of a water bath and measures the change in temperature of the water as the sample burns. By multiplying the mass of water by the specific heat of water by the change in temperature, the molar heat of combustion can be calculated. Delta H equals negative mc delta T.